So a symmetric group is essentially just it consists of all the permutations on a set. So all the ways in which we could just kind of take the elements of the set and scramble them around and see where we end up. Like that's the set of permutations. We call it a symmetric group. Sometimes people will just call it the permutation group. So what we do is we consider the set that has n elements, and we look at all the ways we could permute those. So let's just start by examining S3. So we'll start with the set 1, 2, 3. Now this itself is not the group. The group is going to be all the ways we could permute these. So in every group, of course, there's an identity element. And for a symmetric group, or for a group of permutations, the identity is going to be the permutation that just leaves everything where it is, right? That doesn't change anything. And so I'm going to indicate these elements in, it sort of looks like a matrix, I guess, but I'm going to have these elements, 1, 2, 3, and down below I'm going to indicate where this permutation sends each one. So if the identity doesn't change anything, then this is just going to be 1, 2, 3, because it sends 1 to 1, and it sends 2 to 2, and it sends 3 to 3. Another possible element, another permutation, might be the one that leaves 3, that sends 3 to itself, but maybe just switches 1 and 2. So it sends 1 to 2, and it sends 2 to 1. And there's a couple more elements like this one, right? So here's the one that left 3 alone and permuted 1 and 2. We could also leave 2 alone and permute 1 and 3. We could also leave 1 alone and permute 2 and 3. What's a permutation we haven't looked at yet? Yeah, when they're all, changed, right? Sent to another element. So maybe we could have 1 is sent to 2, 2 to sent to 3, and 3 to sent to 1. That's kind of a very orderly way to go about it.
You can go in the other direction. So 3, 1, 2.
3, 1, 2, like that? Yeah. Yep, 1 is sent to 3, 2 is sent to 1, and 3 is sent to 2. And I think this is it, because I don't think there's any others that mix all 3 up, right? We had, if it's gonna mix all 3 up, 1 is either gonna go to 2 or 3, right? 2 is either gonna go to 3 or 1, and 3 is either gonna go to 1 or 2, and I think we have all of those represented here. So it looks like we have 6 elements, meaning that the order of the group S3 is 6. Now this is sort of a big kind of space invasive, or what's the word I want to use? It takes up a lot of space just to write these 6 elements out. There's we're going to look at a much more efficient way to write out these elements. So we call this using a cycle decomposition. So essentially, if we could represent a cycle, like if we write a cycle like this, A1, A2, blah, 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 AM, that cycle represents the permutation that sends A1 to A2, that sends A2 to A3, right? It's like a chain. And that's sort of how we read it. So let's suppose we have an element sigma. We often use Greek letters to represent elements in a permutation group. That sends 1 to 2, and it sends 2 to 1, and it sends 3 to itself. So in a cycle decomposition, first I'm gonna write it out the old way. So it sends 1 to 2, 2 to 1, and it fixes 3. So the cycle decomposition would be it sends 1 to 2. And now, when I look to see where it sends 2 back to 1. That's how I know I close off the cycle. That's why we call it a cycle decomposition, right? Because it'll eventually go back to the beginning. And then 3 gets sent to itself. So there's like a little cycle with just one element. Now, if an element is fixed by a permutation, so I have this like singleton inside of parentheses, we usually just leave this off. And so our cycle decomposition in its final form would just look like 1, 2. If an element does not appear in the cycle decomposition, it is understood that it is fixed. So just comparing, these two, this is sort of why we adopt a cycle decomposition, the cycle notation, is because this way to express the element sigma certainly a little bit more efficient than writing it the old way. So now, let's say, we have these 6 elements that we came up with at the top of the first page. Let's just write each of these in as a cycle decomposition form. So first we have the identity, and now we have to write something for an element. So the identity we just write as 1 inside the parentheses. Every time, all the elements have to be written inside some sort of set of parentheses. So there's our 1 element. And then we have the sigma element that we looked at before, 1, 2. If we go back to, you can keep referring back to that previous page, but we had the element, so this is the one that leaves 3 where it is and interchanges 1 and 2. We could have the one that leaves 2 where it is and interchanges 1 and 3, and we'd write it that way. What about the one that leaves 1 where it is and interchanges 2 and 3?
Would just be different.
Yeah. So that accounts for all the elements that fix 1 element. Now I'm going to go back up here. What about this guy? How would we write that as a cycle? Yeah. So because we do, 1 gets sent to 2, so we follow up with 2, and then we see where does 3 get sent to? Where does 2 get sent to? That gets sent to 3, so that's our next one. 3 gets sent to 1, and so that means we go back to the beginning, and that's how we know we close off the parentheses. And what about the last one?
It would be 3, 1, 2.
3 gets sent to... 3 does not get sent to 1. So let's start with 1, right? Like if a cycle contains 1, usually we start with that element. So where does it send 1?
2, 3.
Yep. And where does it send 3?
Out of 2.
And where does it send 2?
Back to 1.
So that's when we close. Yep. So those are our last 2 elements. So there's our symmetric group on 3 elements. It's a group of order 6. So 6 elements total. We could see why this is going to be the case. We call it a permutation group for a reason, right? So it's defined, the elements are defined by where it sends each of the elements. So let's look at how many choices. So like we have our elements 1, 2, and 3. If I'm picking like an arbitrary permutation, right? How many choices do I have? Let's think of where we could send 1. How many choices do we have? You know, we're working with the set. By the way, this is our set of 3 elements. I want to send 1 to one of those elements. How many choices do we have?
2.
No.
You can keep it in the same spot, so you 3
Yeah, because remember, some of our elements fix an element. Like, for example, that guy fixes 1, right? So yeah, we have 3 choices for where we could send 1. So then I've picked where I'm sending 1. How many choices then do I have to send 2? 2, yes. And then once I've picked where I'm going to send 2, there's only 1 remaining choice for what I'm going to do with 3. So that gives us a total of 6. This is the same as 3 factorial, right? If we're permuting a set of objects, right, you have however many choices there are for the first element, and then we have like 1 fewer each time as we move on down the line. So let's expand that a little bit. How many elements are there of Sn? So think of, I've got this set of n elements. What's the size of this symmetric group?
N factorial.
Yeah. So the symmetric groups get very big very fast. Little typo here. Sorry about that. This should be S sub 13, not S sub 1 times 3. So let's say we are looking at an element of the group S13. So this is a permutation on these 13 elements. And it's defined, I've written it out a very long way here. You know, 1 gets sent to 12, 2 gets sent to 13, and so on. So we just listed where it sends each of these elements. Let's find the cycle decomposition. And we'll probably do this in a couple of steps, but I always start by, I just start chasing elements through. I always start with 1. Might as well start with the first element. Where does it send 1?
To 12.
Yeah. 1 gets sent to 12. And now, since I'm at 12, then I pick up at 12. Right? And I say, look, it sends 12 to 8. So that's my next one. And then, so we're kind of like connecting the dots, or like kind of leapfrog here. So where does it send 8? To 10, yep. And then where do we go from here?
To 4.
We go to 4, because 10 gets sent to 4. And then what?
Back to 1.
Back to 1, so we close off this cycle. Now we're not done, like there's a bunch of elements we haven't accounted for. So what that means is this cycle, we're just not done with the cycle decomposition. There's an additional cycle we need. So I'm looking through this, I'm looking at the elements that I have in this first cycle. I'll notice that 2 is not in there, so that's where I'll start my next one. Where does it send 2?
To 13.
Sends 2 to 13, and then 13 gets sent back to 2, so we close that off. Still some things not accounted for. I'll notice 3 is not in any of these. So I'll start a cycle with 3. What happens to 3?
It maps to itself.
Yeah, so that just is nothing going on there. Now 4 is already in the first one, so I don't need to start a cycle there. So we'll pick up at 5. Yeah, so so Tim just finished off the cycle for us. 5 gets sent to 11, and 11 gets sent to 7, and 7 gets sent back to 5. So we close that off. And then anything else not accounted for here?
6.
6. Where does 6 get sent?
9.
And back. And then I think that's it. So I'm just going to do a quick count because we should have all the numbers from 1 to 13 here. 1, 2, 3, 4. Yeah, so it looks like they're all accounted for. Now the last thing that I'm going to do quickly is, we found all these cycles that are part of the cycle decomposition, but again, any cycle of length 1 we omit. So I'm just going to eliminate that one. It's not that it's incorrect to include it, it's just sort of redundant to include a cycle that fixes an element. So this is sort of the simplest way to express. It is possible to express every element of a permutation group, we say, as a composition of disjoint cycles. Right, so these cycles, there's no overlapping with each other, right? 2 is in 1 and only 1, right? 5 is in 1 cycle and only 1 cycle. It is always possible to represent a permutation as a composition of disjoint cycles. Now, we know how to denote these. We know what these elements do, what these elements are, right? They're sort of actions, right, on a set. We're letting, we're looking at all the ways we could just sort of rearrange the elements, a set of 13 elements. And those are the elements of this group. Now, if we understand what these elements are, now we kind of have a way to denote them, and we know what the identity element is. The next sort of natural thing would be to examine how do these elements interact with each other. Like, what's our operation? How do we, because that's a big part of being a group, is you could take 2 elements, you smash them together, and you get another element in the group. So we're going to compute these products in the symmetric group. The product, like finding the product, is a fairly simple procedure. I still kind of use my fingers as I go through. You just kind of trace where elements get sent. The important thing to remember is that elements get sent, we read it from right to left. So that's the big thing to remember here. Now, we could just write a product as it is, but we know it's always possible to represent an element as a product of disjoint cycles. And of course, these are not disjoint, they overlap. So I know that there's a simpler way to represent that. So here's what we do. I'm going to first figure out where 1 gets sent. And so I'm reading from right to left. I stop and I say, oh, I get to 1. 1 gets sent to 2. And then I keep going backwards and I say, oh, look, now 2 gets sent to 3. So that means 1 gets sent to 3. Now that I'm at 3, I go again. I start reading backwards until I get to 3. 3 gets sent to 4, and then I go back to see if 4 gets sent anywhere else, and it does not. So 3 gets sent to 4. And now that we're at 4, we start the process again, and we say, okay, well, let's, 4 gets sent to 3, and then I keep going backwards, back, until I come up with a 3 again. 3 gets sent to 1. And so that means 4 gets sent to 1, and we close out this cycle. An element that's not represented here is 2. 2 gets sent to 1, and 1 gets sent to 2. So 2 is just a singleton here, which means that overall this product is just the single cycle 1, 3, 4. Let's try another one. So let's find this product. Where should it send 1?
To 3.
It first sends 1 to 3, but then we chase it back, and
Goes
we
to 2.
and we notice 3 gets sent to 2 here, so 1 overall gets sent to 2. And now that I'm at 2, we can examine where does it send 2.
Three, right? Is this first from the right go to 2 goes to 3?
Well, from the right, so when we read right to left, right, we pick where 2 shows up in the rightmost, right? So
Yes.
that's definitely the 2 we want. But in this cycle, 2 gets sent to 1.
Oh, so you would go from the rightmost to, or wherever you are to the leftmost of that parenthesis? That,
Yeah, like, so in a cycle, this wraps around,
oh, okay.
right? Like 1 gets sent to 3, 3 gets sent to 2, and 2 gets sent to 1 in a cycle.
Okay.
So when we read it right to left, it just means we're picking the rightmost 2 first. This cycle will send that to 1.
Okay.
And then what does it do to 1?
Does it go anywhere?
Yeah, like, so it sends it to 1, and then I keep moving back, and 1 doesn't show up anywhere else. So that means 2 gets sent to 1, and we close off those parentheses. How about, what does it do to 3? How about Curtis? Do you have do you know where it sends 3?
I was gonna say it sends 3 to 2.
It sends 3 to 2 first, right? And then we follow it back to be on the lookout for another 2, and we get one here.
So does it send 3 to 2 or does it send 3 to 3?
That's a good question. Does this send 3 to 2 or does it send 3 to 3?
It's 3, 3.
It sends 3 to 3 because this guy sends 3 to 2, and then we have to follow back and be like, okay, well now where does it send 2? This one sends it back to 3. So that closes it off. It sends 3 to 3. If it did send 3 to 2 overall, I might that would prompt me, or if I wrote down that this sends 3 to 2, then I could just I'd stop and take a breath and like look at my result, and I would know something fishy is going on, is because if my overall product ended up looking like that, when we're done finding the product, we should be looking at a product of disjoint cycles, right? And so the fact that a 2 showed up in both of these would let me know that something is fishy. And of course, anytime we have a permutation that fixes an element, we usually leave that cycle off, so we would just write this as 1, 2. How's that so far? So we know how to kind of put elements together. We know that our identity element is the thing that leaves everything where it is. So now we can just talk a little bit about inverses. And an inverse of the element, if we think of these elements as just as actions on a set, that's a permutation. It just jumbles them up. The inverse should be the thing that unjumbles them, right? Puts it back where they were. If we have an element written in a cycle decomposition, right, in the cycle notation, figuring out what the inverse is as simple as just writing the elements in reverse order, like reversing the order in each cycle. So if this here is an element in S13, I guess, there's our sigma element, then sigma inverse is going to end up being, I'm just going to write each of these cycles in reverse. So 4, 10, 8, 12, 1, 13, 2, 5, 11, 7, 6, 9. We could leave it there. It's usually pretty customary to start each cycle with the lowest number. So in particular, like this first one, if I wanted to write it so that it starts at 1, how would it proceed from there?
It would go to 1, 4, 10.
Yeah. Yep. 1, 4, 10, 8, 12, and then 2, 13, and then the 5, 11, 7 stays as it is, and 6, 9 stays as it is. The last thing I just want to mention about this, and I know it's that there's not an additional page for this, but just a quick result. We're not going to prove it or anything. It would take it would take a lot to prove, but a result, kind of the reason why I just wanted to squeeze in a little bit on symmetric groups at the end, is a result called Kaylee's theorem. And Kaylee's theorem says that every finite group is isomorphic to a subgroup of some Sn, of some symmetric group. And in particular, if the order of G is n, then G is isomorphic to a subgroup of Sn. I mean, through this lens, we could sort of think of every group as a group of like actions on a set, right? I mean, the symmetric, these permutations that we're looking at, they're really just actions on a set, right? Ways in which we can jumble them up. And if every group is isomorphic to a subgroup of Sn, we could think of every group as just being a collection of things that could act on a set. And that can kind of reveal a lot about the structure of a group.